Okay, this lecture is over the ARP protocol. ARP stands for Address Resolution Protocol, and the purpose of ARP is to resolve addresses to find a MAC address that corresponds to a given IP address. And the reason we need to do this is most communications are IP packets, but as you should know, when machines need to communicate with other machines on the same network, or possibly the default gateway, which is on the same network, it needs to do that by MAC address. So basically, we discussed this briefly before under address forwarding, because what happens when a packet needs to be forwarded off the local off the local network, which is what we were talking about in that context. So basically what happens is the machine that wants to communicate, that I'm calling the sending host, it sends out an ARP packet, and it's a broadcast. So it goes to all machines on the local network and basically says, hey, here's my IP address and my MAC address. I'm looking for the MAC address of the machine with IP address x.x.x.x. So whatever machine or address it wants to communicate with. Now, machines that do not have the requested IP address just simply ignore the ARP request. However, the machine that does have that IP address responds back with, hey, that's me, here's my IP address and my MAC address. And it will add an ARP entry for the machine that sent out the ARP request. That gets transmitted out. The machine that initiated the ARP process will see that response. It has the information it needs, namely the MAC address, and it will enter the IP address and MAC address for the particular machine in its ARP table or ARP cache, and we'll talk about that a little later in this video. So this is the ARP packet structure. An ARP packet is 28 bytes in length, and here are all the fields shown. We'll go through them one by one and talk about what they mean. The first thing is the hardware type. It was 2 bytes. That basically tells what type of hardware sent the ARP packet. And most of the time in today's world, we're going to see a 1 there, which means it was sent over Ethernet. The protocol type specifies the type of layer 3 addresses that we're going to be using in the message. And again, most common will be 800 hex, which means we are sending an IP packet basically. The hardware address length is 1 byte. It is the number of bytes in the hardware address. So for an IEEE 802 MAC address, this is going to be 6 bytes, or as you probably know, the way I've asked the question previously, 48 bits. I think I've mentioned this before, but IEEE is the Institute of Electrical and Electronics Engineer, and IEEE 802 is a set of standards for computer networking. The protocol address is the number of bytes in the layer 3 address, and for IP version 4 this is going to be 4 because 32 bits is 4 bytes. We then have an opcode that specifies the type of ARP message being sent. For normal ARP, 1 implies this is an ARP request, that is, I'm asking for somebody's MAC address. A 2 implies that it is the reply. So somebody asked me for my MAC address and I am sending it to them. So we have kind of a request reply type situation that we discussed. We have the sender's hardware address. This is the number of bytes specified in the address length field. So if it was 6, there would be 6, and this is the hardware address, which is another term for MAC address of the device. The sender protocol address is the number of bytes specified in the protocol address. So I think the example said IP version 4. There are 4 bytes there, so there would be 4 bytes, and this would be the IP address of the sending device. The target hardware address is the length of it is the number of bytes specified in the hardware address length field, and this is the IP address of the destination device on a request, or the source if we're talking about an ARP reply. Target protocol address is the IP address of the device the message is being sent to. So in this class we'll be delving a lot into kind of real life examples. So what we have here is a frame that I captured with Wireshark, and if we look at the whole frame, we have 60 bytes that were captured. We have the whole thing highlighted to the right. Just real quick, we'll look at the layer 2 information. So we have a destination MAC, a sending MAC, and the type of enclosed packet. Notice that the type of enclosed packet, we've been seeing 800, which is IP up to now. This is 806, which corresponds to an ARP packet. So if we look a little further and actually look at the ARP packet, over in the left we have the address resolution protocol selected. Notice it tells us it's a request, and it highlights everything in blue that is part of the packet. So as I showed you in the example, the hardware type is highlighted. A 1 value means this was Ethernet. The protocol type is 800, which is IP version 4. The hardware size is 6, which means it's 6 bytes, which means we have a MAC address. The protocol size is 4, which means we have 4 bytes because this is an IP version 4 address we're looking at. The opcode is 1, which means this is a request. Here's the sender MAC address. Here's the sender's IP address. And then here we have the target MAC address. And since this was a broadcast, we're not sending to a single machine. So that's simply just filled with zeros. And then this is the target IP address, or the IP address we were looking for. And if you change that into decimal dotted notation, I was looking for 128.163.9.161. Now then, we have a minimum size of a packet. So what happens is this packet is padded out to the 46 bytes that we need. So in this case, there are 18 bytes of padding, which are just set to 0. So that's the ARP packet. The packet we discussed was an ARP request. Let's look at the ARP response for that packet. So I was looking in Wireshark in the main window, the packet list window, and 393 is the response to the broadcast ARP request in 392. So you'll notice the question kind of here in, I guess, a light brown. Who has 128.163.1.6? Tell me. And then it came back and a machine responded and said 128.163.1.6 is at this MAC address on the local network. So that is the ARP response. And if we go look at this in the packet details and the packet byte window, which are side by side, this is what we see. Notice where it says address resolution protocol, we had a request before. This, of course, is the reply. If we go through and look at this in detail, again, this is an Ethernet transmission, so the hardware type is going to be 1. The protocol that we're using is IP version 4. The hardware size, the MAC address is 6, so we're telling it there. The protocol size is 4 because we're dealing with IP version 4 addresses. The opcode is 2, so 1 was a request, 2 is a response. Here's the MAC address of the sending machine. Here's the IP address of the sending machine. This is the target MAC address. Notice this time this is targeted to a specific machine. So instead of having a bunch of zeros like we did before, we actually have a MAC address. Here's the IP address of the machine. And like before, we still have to have some padding to make this packet 60 bytes in size. Or because the minimum frame size is 46. In the list of topics, there was something called ATM ARP. I can't remember if I mentioned this or not, but ATM has been obsolete since the mid-90s. That being the case, I could not find any information other than to mention that ATM ARP packets are very similar to ARP packets. So I don't know if they are truly the exact same thing or if they're similar in nature. But we're not going to worry about this because it's such an old protocol. However, there were some topics that were not listed specifically in the course topic list that I would like to talk about. And those are reverse ARP, ARP caching, and proxy ARP. So RARP stands for reverse ARP. Like I said, in the case of ARP, we have an IP address and we want to know the MAC address. Well, this is the reverse. So what happens is we have a MAC address and we want to find the IP address of the device. There was something in the 70s and 80s that was heavily used called BootP. This is considered to be the predecessor to ARP. Basically, BootP was for booting diskless devices. So a lot of times you had workstations that had memory and compute and a display, but they didn't actually have a hard drive. So what happens is you would go through, and when you turned on one of these diskless devices, they would broadcast, hey, this is my MAC address. Does anybody know anything about me? And two of the most important things you could get would be an IP address to use and where your boot file existed on the network so that you could download your operating system. So a BootP server would come back if it knew its device, and by knowing the device, that means it had information in a file called a BootP tab, usually in /etc on a server somewhere. The ARP question is, I am device X, can somebody tell me my IP address? The question is sent in an ARP packet with an opcode of 3 and a 4 for the reply. So it would get that information via the reply. Now then, ARP caching, I mentioned that both machines in the ARP process would store that information, and that's called a cache. So what it's going to do is, the assumption is, if I talk to a machine once, just one packet, it's very likely I'm going to talk to that machine some more in the near future. So let me go ahead and store the hardware address for a given IP in my table or in my cache. And that way, when I need it next time, I can just do a lookup instead of doing a broadcast out on the network and trying to get a response. So that's the reason behind caching. When it puts that information in the ARP table or the ARP cache, it sets a timer for how long that entry will stay in the cache. On my machine, it appeared to be around 2 minutes. Every time you communicate with that IP again, the timer is reset to the maximum value. Again, the assumption is if you're talking to this machine, you will probably continue talking to it for a while. If that time ever reaches 0, then that entry is removed from the ARP cache. If in the future you need to talk to that machine again, it'll go through the full ARP process and recache the address. The most common ARP command to issue on a machine, regardless of whether it is a Unix, Linux, or Windows machine, is ARP-A. I did this on my Mac machine and terminal, and this is what I got back. So it'll have IP addresses, hardware addresses you need to talk to, and which interface you need to go out. And my main interface is EN0 on my Mac. If you care about the timers, you add an X option to the command. So ARP-AX will give me something that looks like that. So you can see that some of them are expired and haven't been removed yet. Some of them have anywhere from like 5 seconds to 1:49 to go. So if you need the timer information, this is how you get the timer for entries in the ARP cache. Sometimes you put static or permanent entries in an ARP table. This is primarily to do with routing, where you have a machine or network that you want to communicate that would not be learned. Or where I used to use this was during the 80s when I would dial up and connect PPP from my next machine at home to my next machine in my office. So basically on my home machine, it's like packet going anywhere, send it to my work machine. And then my work machine would know how to route it out onto the internet. So basically that put me on the internet so that I could communicate. Another thing that sometimes you need to know about is proxy ARP. Basically, this is where you have a proxy server on the local network that is going to answer ARP requests that are for IPs that are on other networks. This can make clients on different networks appear as if they're on the same subnet as you without having to go through and change a subnet mask or re-IPing machines or that type of thing. So if you have a very large enterprise, sometimes this is a very helpful thing to do. So that's the discussion on ARP.